Welcome back to G Fun Facts Online. Today, we are going to dismantle the single biggest misconception about the red planet. For centuries, astronomers gazed at Mars and saw a desolate, rusty wasteland, a global desert where dust storms raged and liquid water was a phantom memory from billions of years ago. But that image is shattering. Beneath the ruddy regolith, Mars is hiding a secret that changes everything: ice. Not just frost at the poles, but vast, continent-sized glaciers buried under equatorial dust. Ancient fossilized oceans trapped in rock, and pure, massive slabs of frozen water just meters below the surface. This is not merely a scientific curiosity, it is the single most important factor for the future of humanity in space. We are no longer looking at Mars as a place to visit, but as a place to live. And to live, we need water. The recent discoveries of massive subsurface ice deposits, particularly near the equator in the Medusae Fossae Formation and the dramatic Noctis Labyrinthus, have rewritten the playbook for colonization. We no longer need to haul our own water across the cosmic void. It is already there, waiting for us. To understand the magnitude of recent discoveries, we must first unlearn the dry Mars dogma of the 20th century. While the Viking landers of the 1970s showed us a bone-dry surface, the orbiters of the 21st century, equipped with radar eyes that can see deep underground, have revealed a planet that is surprisingly wet, provided you know where to look. For decades, mission planners faced a cruel dilemma. They wanted to land human crews near the Martian equator because that's where the sunlight is strongest, which is essential for solar power, and where the temperatures are mildest. However, they believed all the accessible water ice was locked away at the freezing, dark poles. It seemed we had to choose between power and water. That changed with the startling data from the European Space Agency's Mars Express orbiter. Its MARSIS radar instrument probed the Medusae Fossae Formation, a mysterious, wind-sculpted region of soft rock extending for 5,000 kilometers along the equator. Scientists had long debated what the formation was made of. Was it volcanic ash? Porous dust? The latest analysis, released in early 2024, delivered the verdict. It is ice, massive amounts of it. The radar signals indicated a material that was low in density and transparent to radio waves, a signature that matches water ice perfectly. The deposits are colossal, stretching up to 3.7 kilometers or 2.3 miles deep. If this ice were melted, it would cover the entire planet of Mars in a global ocean between 1.5 and 2.7 meters deep. This is the largest deposit of water ever found near the Martian equator. This discovery is a strategic game-changer. It means future astronauts could potentially land in the tropical latitudes of Mars, set up vast solar arrays for power, and still have access to essentially infinite water reserves beneath their feet. The catch? It is buried under hundreds of meters of dry dust and ash. But its existence proves that the equator is not the dry trap we once feared. While Medusae Fossae offers deep reservoirs, a more accessible treasure was found in the labyrinthine canyons of Noctis Labyrinthus, just west of the colossal Valles Marineris canyon system. In 2024, scientists announced the discovery of a relict glacier, a massive sheet of ice that had been preserved just beneath the surface, protected by a blanket of volcanic salts. This discovery was serendipitous. Researchers were studying a newly identified volcano in the region when they spotted strange geological features: rootless cones, caused by steam explosions and light-toned sulfate deposits. These sulfates are significant because they form when volcanic ash interacts with ice. The salt crust effectively fossilized the glacier, preventing it from sublimating or turning from solid to gas into the thin Martian atmosphere. Unlike the deep Medusae Fossae deposits, this glacier might be accessible with shallow drilling. It sits in a region of chaotic terrain where the crust has fractured, potentially offering skylights or easy access points to the ice below. For a human settlement, this is the Holy Grail, a location with interesting geology, volcanic heat sources potentially indicating geothermal energy, and shallow, harvestable ice. Further north, the evidence for ice becomes even more direct. In regions like Utopia Planitia and Amazonas Planitia, NASA's Mars Reconnaissance Orbiter has used its shallow radar to map ice sheets that are the size of New Mexico and hold as much water as Lake Superior. Here, the ice is not kilometers deep. It is practically scratching the surface. In some areas, erosion has created scarps, steep cliffs that have sliced through the terrain to reveal the cross-section of the ground. These scarps show banded layers of pure blue ice, some over 100 meters thick, beginning just a meter or two below the red dust. These scarps are essentially road cuts made by nature. They allow us to see the resource without drilling a single hole. For a first-generation colony, these northern mid-latitude sites offer the path of least resistance. You wouldn't need heavy industrial drills. You could practically excavate the ice with a backhoe. So, how do we know this ice is there if we haven't touched it? The story of Martian ice is a triumph of remote sensing physics. It relies on the interplay between electromagnetic waves and matter. Ground-penetrating radar is our primary tool. instruments like MARSIS on Mars Express, and SHARAD on the Mars Reconnaissance Orbiter beam radio waves down to the planet. These waves pass easily through dry dust and rock, but reflect sharply when they hit a boundary between different materials, like the transition from rock to ice. By measuring the time delay of the reflection, scientists can calculate the depth. By analyzing the strength of the reflection, they can determine the material. Rock absorbs radar energy differently than ice. The signals returning from medusae fossae and the polar caps are distinctively transparent, meaning the radio waves pass through them with little attenuation, a classic signature of pure water ice. While radar sees deep, neutron detectors taste the surface. The ExoMars Trace Gas Orbiter carries an instrument called FRIEND. It detects neutrons that are knocked loose from the Martian soil by cosmic rays. Here is the physics trick. Hydrogen atoms are excellent at stopping neutrons. Since water is rich in hydrogen, wet soil absorbs more neutrons than dry soil. FRIEND creates a map of neutron suppression. Dark spots on this map, where fewer neutrons bounce back to space, indicate areas where hydrogen is abundant in the top meter of soil. This instrument recently revealed that the massive Valles Marineris Canyon system is packed with near-surface hydrogen, likely in the form of chemically bound water or ice, covering an area the size of the Netherlands. And sometimes, you just need a good camera. The HiRISE camera on the MRO is a spy satellite for Mars, capable of resolving objects as small as a coffee table. It has captured images of fresh impact craters, where meteoroids have punched through the dust, exposing bright white material underneath. Over the course of weeks, this white material fades, sublimating away into the atmosphere, visual proof that it was water ice, not stable rock. Finding the ice is step 1. Getting it out of the ground in a -60°C vacuum is a monumental engineering challenge. You cannot simply chip away at it with a pickaxe. The ice on Mars is as hard as granite due to the cryogenic temperatures. Furthermore, if you expose it to the air, it won't melt into a puddle. It will flash boil into vapor and vanish. Engineers at NASA and private companies like Honeybee Robotics are developing specialized technologies to solve this, borrowing techniques from Antarctica and the oil and gas industry. The leading concept is the Rodwell. The Rodriguez well, or Rodwell, is a technology developed by the U.S. Army in the 1960s to provide water for Camp Century in Greenland. The concept is elegant in its simplicity. Instead of mining solid ice, you melt a cavity underground. You drill a shaft down into the ice sheet, pump hot water or steam down the pipe, and let the heat melt the surrounding ice, creating a pool of water deep beneath the surface. You then pump the liquid water up, reheat a portion of it, and send it back down to melt more ice. On Mars, a Rodwell is ideal because the well stays underground. The liquid water is never exposed to the low-pressure atmosphere, so it doesn't sublime. The overlying dust layer acts as an insulating lid, keeping the heat in. Adapting the Rodwell to Mars requires miniaturization. Enter RedWater, a system designed by Honeybee Robotics. RedWater replaces the massive drill rigs of Earth with a coiled tubing system. Imagine a drill pipe that is flexible, like a garden hose made of steel, wound onto a large spool. This allows a compact lander to deploy a drill capable of reaching 25 meters or deeper without needing a tower crane. RedWater drills through the abrasive dry soil using gas jets to clear cuttings. Once it hits the ice, it switches modes, circulating hot water to melt a bulbous cavity. It is a dual-use probe, a drill to get there, and a well to harvest. For shallower deposits, some visionaries propose optical mining. This involves using mirrors to focus sunlight onto the icy ground. The concentrated solar energy heats the regolith, causing the ice within it to sublime. The resulting water vapor is captured under a tent, funneled into cold traps, and condensed back into liquid. This method has the advantage of having no moving parts, just lightweight mirrors and thermodynamics. This leads us to In Situ Resource Utilization, or ISRU. This acronym basically means living off the land, and it makes colonization possible. Water ice is the feedstock for the 3 pillars of survival: air, water, and fire. First, the breath of life. By running an electrical current through water, we split it into hydrogen and oxygen. The oxygen goes into the habitat's life support system. The hydrogen is saved for the next step: rocket fuel. You cannot bring enough fuel from Earth to fly home from Mars. The rocket would be too heavy. You have to make your return gas station on Mars. This is done using the Sabatier process. We take the hydrogen from the water electrolysis and mix it with carbon dioxide sucked from the Martian atmosphere. The result is methane, the most efficient rocket fuel for deep space, and water, which is recycled back into the system. SpaceX's Starship is designed specifically to run on methalox, which is methane plus oxygen, for this exact reason. Every Starship that lands on Mars will be a chemical plant, thirsty for hundreds of tons of ice to refuel for the journey back to Earth. Finally, there is agriculture. Martian soil contains toxic salts called perchlorates. However, if we wash the soil with our harvested water, we can flush out these toxins. We can then use the water for hydroponics, turning the ice into tomatoes, lettuce, and potatoes. The water becomes the blood of the colony's ecosystem. When we think of Mars habitats, we usually picture metal tin cans or stone igloos. But architects are proposing a radical alternative: buildings made of ice. Mars has no magnetic field and a thin atmosphere, leaving the surface exposed to galactic cosmic rays. To be safe, astronauts need shielding equivalent to about 3 meters of concrete. Hauling concrete to Mars is impossible. But water is an even better radiation shield than concrete, because hydrogen atoms are unparalleled at blocking these rays. The Mars Ice House concept proposes a translucent habitat. Instead of living in a dark, buried bunker, astronauts would live inside a pressure vessel, surrounded by a thick, 3D printed shell of ice. Ice blocks radiation but lets in visible light. Robots would harvest subsurface ice, melt it, and print it layer by layer around the habitat, where it would freeze instantly. This allows astronauts to enjoy natural circadian rhythms and views of the Martian landscape without being irradiated. The discovery of ice also brings us back to the ultimate question: are we alone? On Earth, wherever we find water, we find life. Dusty ice on Mars creates a fascinating microenvironment. When sunlight hits dust grains trapped inside the ice, the dust heats up, melting a tiny pocket of water around it, even if the air temperature is far below freezing. This is called the solid-state greenhouse effect. These cryoconite holes could be safe havens for Martian microbial life. This brings us to the concept of planetary protection. The Committee on Space Research, or COSPR, sets international guidelines to prevent contaminating Mars with earthbugs. Regions with accessible water ice are classified as, quote, special regions. These are areas where terrestrial microbes could potentially replicate. Under current strict rules, we are technically forbidden from sending dirty human explorers into these zones. This creates a tension. The places we need to go for resources are the exact places we are banned from going to protect science. Resolving this will require new technologies for sterilization, and perhaps a philosophical shift. And then there is the law. When a starship starts pumping water from the ground, who owns it? The Outer Space Treaty of 1967 states that outer space is not subject to national appropriation. No country can plant a flag and claim the ice fields of Utopia Planitia. However, the Artemis Accords and US law argue for a distinction. They say that while you cannot own the land, you can own the resources you extract. It's like fishing in international waters. You don't own the ocean, but you own the fish you catch. Not everyone agrees with this, and as ice becomes the oil of the solar system, conflicts could arise. We will likely see the emergence of safety zones around mining operations. The ice of Mars will force humanity to write the first constitution for an interplanetary civilization. The discovery of hidden ice on Mars is the turning point in our relationship with the Red Planet. It transforms Mars from a scenic backdrop into a destination with logistics support. We have the map, we have the technology, we have the architectural vision. The challenges that remain are engineering and political, not fundamental physics. Generations from now, when Martian children look out through the translucent ice walls of their homes, watching the sun set over the rim of Valles Marineris, they will not see a dry, dead world. They will see a world that gave them the water of life, a world that was waiting for them all along, wrapped in a blanket of dust. The ice is the key, and the door is about to open. Thanks for listening to G Fun Facts Online.